All right, so thanks for moving over. I guess not too many people can show up because this room's smaller, so it's probably work out.
Might not be a problem.
Yeah, I don't think that'll be the major issue today. So today we're primarily going to be talking about analog digital converters, ADCs. I'm also going to recap some improvements to the metal detector you would have experimented with in the lab a little, in terms of how to get a stronger signal and more sensitive. All right, and I'll also talk about DAC, digital to analog converter, which is something you can do with some of the parts in your kit, and most importantly, using the actual ADCs with your AVR. All right, so metal detector lab. So in the metal detector lab, everything you were doing was using, something like a signal generator, a piece of test equipment that you dialed in the frequency to find resonance and stuff like that. And it was pretty basic. That had some driver in it, and you might have had a resistor going into your tank circuit, like this. Into ground, and then this would go to your envelope detector, and the end result would be some sort of voltage. And depending how well you did the tuning and the size of your inductor and things like that, you could get some somewhat usable signal out of this. A few problems with it were that A, you need this piece of equipment here to do this, so the generator. And B, you probably found that some people had fairly successful results, some people didn't, and you would have to play with this resistor value. Ultimately, what we sort of found out is that if this was, your 10K variable resistor or something like that, you would basically have to, measure what the change in voltage at this point was here when you brought a piece of metal near the coil. And then you could just play with this value until you got the largest change in voltage, and that was sort of the ideal setting for it. The other thing to note was that the foil, a little piece of foil, worked really well for bringing near it to detect. So if you want to test this on the course, you'll shortly be able to get access to the course to see what the metal is on it. But a piece of tin foil, aluminum foil from cooking or whatever, was perfect. But how you can sort of improve this in terms of something you can build on your circuit is that, for starters, you're going to have the AVR, and this can generate a square wave frequency. So you would have done this in the assignment, generating some specific frequency on one of the output pins. So that's something you can do. We need a stronger signal to drive the circuit. So what I would recommend is using either the transistor or the FET in your parts kit. So let's draw this with the FET, however it goes. Actually, it's not. I won't do a MOSFET. I'll just do the regular FET. And if you have ground, and you'll have the same thing. You have a tank circuit here. So this is your tank circuit, this is your coil and cap. And again, you'll have the resistor, the tuned resistor. And then this just goes to, V in. Which could be a regulated 5 volt or something else. So one thing you can do slightly to improve this circuit is actually add a bypass on the resistor. So if you have a capacitor here, and this could be like whatever, 1 microfarad. The exact value doesn't matter. I don't know all the ones in your kit. It could be 0.1 or the 100 nanofarad capacitor or something like that. But this will help improve the Q of the overall circuit, as it'll reduce the impedance the higher frequency signal is seen looking up into the VN port. And then of course here, you would take your output, and these are all grounds. So that sort of circuit should give you a fairly useful metal detector for quite a simple setup. And where you'll use this is that if you remember on the course there was various strips of metal. These strips of metal are actually foil tape because it works so well at detecting it. And your robot can basically, if you have two search coils in front of your robot, let's see if we can make this better. So if you have your robot here, you may have two, you could have two search coils off to the side. And as the robot rotates, it can sense where the metal is. So it can say, oh, I'm about to run over the metal, rotate a bit so I'm not. It's up to you. This is sort of what people have done in the past, or you can just have one search coil in the middle and sort of track back and forth to follow the metal. Of course, it's not needed. There's other artifacts of the course you can use for detection, especially having the compass and the gyroscope in your kit improves your ability to do some of the detection without necessarily relying on this. But it is just one of the features available to you. So if you want to use it, this would be a sort of a good starting point. Again, this resistor you'll have to tune in the same fashion. And once you get it tuned, you should be able to add this capacitor. You'll also have to tune the frequency. So this should be the resonant frequency. And you'll want to do this in the lab, most likely, using the signal generator so you can just sweep through the signals. Finding the resonant frequency to get the maximum amplitude. Once you get the maximum amplitude, you can tune the resistor to give you the best detection. And then add the capacitor, and you should have a working system. All right, questions on that? If not, I already talked about that. I'll move on to the main part of the lecture, analog to digital converters. So very briefly, an analog to digital converter has analog on this side and digital on one side, the other side, the output. So it's converting from an analog signal to a digital signal. So when we say an analog signal, we normally are talking about just a voltage on a wire. So an analog signal really has, infinite. When you talk about what the voltage is, it's 1.2348, and it would just keep going. There's no end. It's not 2.5 volts, and that's it. Of course, when we measure things, we always, have some amount of significant digits we round to. In a similar way, a digital system, though, only has very fixed levels that it can quantize each signal to. So every signal is represented by a number. So this 1.23 whatever volts is represented by 156. 2.3 some volts is represented by 234. So on one side is the real physical world, the voltage. On the other side is our digital world, where we just are talking about digital numbers. So we refer to these numbers as counts, or you'll often hear it referred to this. So 1,024 count. So in this case, there's the ADC could count from some range, so it could be 0 to 255. So 0, 1, 2, 3, 4, etc., up to 255, meaning there's 256 possible counts that it can use. This is really just how many different levels the ADC can represent. So that if you had that 0, 1, 2, 2, 5, 6, each of these numbers represents a different voltage range. So this could be around 0.0 volts, 0.1 volts, etc. And then all the way up to whatever 256 represents using that scale. So the most basic ADC could be a 1-bit ADC. So when we talk about 1 bit, what we're really referring to is that this idea of counts is like a digital number. So if you have a 8-bit digital number, it represents 256 possible states. So if you remember, an 8-bit digital number has 8 binary digits, so that could be one of the outputs of the ADC, is whatever this ends up being equivalent to in decimal. So there's 8 outputs from the ADC. A 10-bit ADC would just have 2 additional bits here, and it gives it even further range. So then this would be 2 to the 10 equals 1024 possible counts or levels. So that would be a 10-bit ADC. A 16-bit ADC would be 2 to the 16 possible different levels it can distinguish between. So the higher the number of bits, the more levels it's distinguishing between. The most basic ADC would be a 1-bit ADC, which would be 2 to the 1 equals 2 levels. And you can use this to sort of get an idea for how an ADC works. In this example, what we have is we have a comparator and we have Vref, so this is the reference voltage. Ref voltage. And then we put an input. This is our analog signal. The output of the comparator will just go to 0 or 1, depending on if the input is lower or higher than that reference voltage. So you can see at the bottom here, let me just move it up because it's way at the bottom of the page. All right, so I'll move it up so it's easier to see in the back. So this would be the output of that 1-bit ADC. What we have is we have the input signal in red, and dotted in blue is what the digital output would be. And this is basically saying that, you know, when the input voltage is below the green reference line, it's outputting a 0. As soon as it passes that reference line, it outputs a 1, and it just stays at a 1 until again there's this point here where the red analog signal is passing below the V reference, and it outputs a 0. Wherever it passes it again, this isn't a perfect diagram, but you get the idea. It goes to 1 and 0. So the output was 0 here, 1 here, 0, 1, and then it would be 0. So the 1-bit ADC, you know, the levels change within it, but the ADC is unable to tell you more information than it's higher than this reference level or it's lower than this reference level. It can't say, you know, is it a tiny bit higher, is it much higher, or, you know, just about to cross. It only tells you higher or lower. In the same way, an ADC with more levels can only distinguish whenever it's in between these levels. It can't tell you within the level what the error is. So in this example, I have an ADC with 5, 6, these 12 levels. So it's not a regular, you know, 2-bit or 3-bit ADC. It's sort of random levels. But what you can see is if I put in this analog waveform here, what you'll end up with is at the output some step-like function. Each of these steps is whenever the input has passed the threshold for one level and gone to the next. So it cannot perfectly represent that input waveform, and you can see sort of the blockiness in it. And that's just an artifact of the quantization error in the ADC. It's unable to fully sort of represent the input because it doesn't have enough resolution. And when we talk about this error, what you'll see a lot is something that's referred to, you'll see this LSB, and LSB is referring to the least significant bit. Basically, if we go back to where we're talking about the binary system and the ADC counts, if you had, you know, an 8-bit or whatever, some ADC, let's say a 3-bit ADC, and it's outputting binary 3, so 0, 1, 1, and that represents some voltage level. The next step is going to be when it outputs 4, so if that, or 2. it's always going to be one more or less than that. So what we call this is a change of one least significant bit. So this is why you'll see all the time referred to, that change of one LSB. What does that mean? Does that mean a 0.1 volt increase in the signal, a 0.5 volt, a 0.001 volt? So it gives you some idea of what the resolution of that ADC is. And if we look at the quantization error, what this graph here is showing is that this is for a 3-bit ADC. So there's 8 possible levels it can represent. As the voltage goes up, so this is input voltage here, as the voltage is increasing, what you'll see is, at 0, it outputs 0, 0, 0. At 1/8 of the reference, it outputs, at that point, it jumps to 0, 0, 1, then 0, 1, 0. So it's just incrementing in a, the binary count as the input voltage goes up, which is what you expect. And at the bottom, you can see the error is going to grow from, initially there's actually no error before it changes because it's outputting 0, it's right at 0 volts. And then it'll slowly go up to a maximum of when it next crosses the LSB threshold and then drop down to 0. So this is sort of what the error looks like for that type of ADC. The other thing you can do is you can actually shift all your offsets down a tiny bit, which, I didn't put that in. But basically, you could have an error graph that goes instead, is halfway, goes from negative half LSB error to half LSB error. So that might be a little better because right now we have this constant bias of half an LSB of error. If you went from negative to positive, you're going to shift that bias to be back down around 0. So one of the things you'll often have to do in the design process is figuring out what number of bits you need in the analog to digital converter. And this is basically where you have to say, do I need 2 to the 8 equals 256 levels? Do I need 2 to the 10 equals 1024? And so on. 2 to the 12 with 4096. Like, how many bits do I need to represent whatever the signal is I'm measuring? And this is one of the major specs in an ADC and drives, what sort of cost, what sort of sample rate you can have. The easiest way to do that is, actually, I thought I had another slide here. Yeah, so there's a few different ways to do that. The ADC, what we call the resolution, is the number of bits. So you can calculate what the signal to noise ratio is that you require from your signal. So if you have certain specifications, like I need to make a CD quality audio or FM quality audio, that defines how much noise you can have in your digitized signal. The quantization error, if we look back here, this quantization error effectively becomes a type of noise, and the higher the number of bits, the lower this noise is. So you can look up a formula to calculate what the exact level of the noise is. But what's more common, I think, is something where you need to calculate the required step. And this will tell you how many bits you need in your entire system. So, I just want to check. Battery's still good here? Okay. So let's go through an example of that. Oops. Yeah, so calculating the required steps. It could be something like if we had, so using something similar to your robot example, let's say we have a rangefinder, and it tells you the distance to an object. And this distance is a digital signal. So the output of this rangefinder is a voltage. And the voltage varies from 0 volts to 1.25 volts. So that's the range that the sensor outputs, and we have a range. Let's say it has a 10-meter range, and what we want is 1 centimeter of accuracy. And I don't know what the sensor is capable of. I'm just saying that's what I want. I want to be able to get a 1 centimeter resolution, really. So I want to be able to differentiate when the sensor is claiming it's moving 1 centimeter. So can our AVR microcontroller ADC do this, or do we need an external ADC? So really, what we're saying is, at the end of the day, if I assume that the output here is 0 volts, range is 0 meters. When it's 1.25 volts, it's 10 meters. And the resolution I want on this thing is, what did I say, 1 centimeter, which is 0.01 meters. So the easiest thing to do is actually say, well, how many steps do I need to be able to discern in that voltage range that I'm measuring? And it's quite simple. In this case, it's just the 0.01 meters. So 1 divided by the 10, or the other way around, sorry. So the 10 meter is the total range. This is the full scale of the device, divided by 0.01. What does that end up? So that ends up to 1,000 counts. So if I can discern 1,000 different steps in the output, I'll be able to obtain that 1 centimeter resolution. So at first guess, it would look like, yes, the AVR, so remember the AVR ADC is equal to 2 to the 10, is equal to 1,024 steps. So it would look like we can just achieve the required the resolution. So there'll be another issue, which is how do we, what's this voltage reference point that we care about? So I'll talk about that. So I'll come back to this example after I cover the next little section here. And that is, what is the VREF voltage for the ADC? So when we looked at the ADC, we were saying the input can go from 0 to VREF. This is the other really critical thing. It's not just that you get these 1,000 counts however you want them. What it is that the ADC, when you use it, so if I draw an ADC here, has an input and it has a VREF. And so the ADC will break the input typically from 0 to VREF. Is broken into buckets. Each of those buckets, if you have the 10-bit ADC, you get 1,024 buckets. So why this really matters is that if your VREF is 5 volts, for example, let's say it's 5 volts, what you end up with is you have 1,024 counts equally spaced between 0 to 5 volts. So what's the size of each of those counts? Well, you can say it's 5 volts over 1,024. So is about 4.88 millivolts. So each step in the ADC outputs represents, a little under 5 millivolts change. Now, if you needed, maybe this isn't enough resolution. You still have the same 10-bit ADC, but you need higher resolution. And this is where it depends a lot on your signal, what the signal levels are. Because maybe my signal only goes up to 1 volt, in which case the easiest thing to do would be to say, well, I could make 0 to VREF, and let's make VREF just equal to 1 volts. And we still have the same 1,024 counts. But now, the step size is this 1 volt over 1,024. What's that? So 0.977 millivolts. So all of a sudden, basically the step size has been divided by 5, which is what you'd expect. But you may have to tune what this VREF is to get the amount of sort of resolution you require at a volt scale out of the device. So going back to this example, here, the one caveat would be my sensor output at maximum is 1.25 volts. So if I was using the ADC and I said between 0 to 1.25 volts, I need 1,000 counts. If, for example, I had this top level, the ADC is actually 1,024 counts, but from 0 to 5 volts. So I'd either have to use this ADC, I'd have to set my VREF to that 1.25 volts. I'd have to have some sort of reference for the sensor to get the resolution I'm looking for. Otherwise it won't work, because the 1,024 volts between 0 to 1.25 volts that the sensor is covering, there's only a subset of these 1,024. You can't see that, sorry. A subset of these 1,024 counts in that range. They're over the whole range of the sensor itself, or of the ADC itself, sorry. The other trick when it comes to VREF, one thing you'll very commonly have is, let's say we have a sensor that varies its resistance with temperature. So this is a temperature sensitive resistor. Temp sensitive resistor. And what we're going to do is we're going to use a voltage divider. So if I put this to ground, plus 5 volts, and I have a V out here. And so the output here, the voltage at the output is going to vary depending on the temperature. If the temperature goes up and the resistor goes down, that output voltage is going to fall, just based on that voltage divider. So I'd like to measure that in my ADC. So the easy thing to do would just be to say, okay, well, let's just plug that right into our ADC, and we have VREF here somewhere connected, and it goes to some reference voltage. The problem is that nothing in life is perfect, so these voltage regulators aren't going to be exact. Maybe you end up with 5.1 volts. It's just a few percent, 5%, 10% accurate. So this input voltage is not what you expect, therefore there's an offset on this, this voltage here. So when you go to measure it in your ADC, you get some error. A really easy way to fix this is sort of one of two ways. One way is to actually use the power supply that you're powering the sensor with as your VREF. What we've done now is the ADC reference voltage is always relative to this divider. The output here is really just related to what the input voltage is, and now the ADC count is also related to, or the supply voltage. It no longer is in absolute terms. One ADC count is 4.35 or 3.88 millivolts or whatever. Now one ADC count is 1/1024th of the VREF, and that VREF is the same thing that's saying this goes to our voltage divider. So this sort of eliminates a little bit of error in your system design. So that's one way to do it. The other thing you could have done is you could have said, and it depends how you do this, depends on sort of what your specifics of your system are, but it will be equivalent, is if you use a buffer here. And so we just take the VREF. It's doing the same thing. If we had the VREF connected to something else and we couldn't change that, we're just going to take that VREF and use it with a buffer to actually power a resistive sensor network here. So the objective is the same, though the ADC reference voltage is related to this, this resistive divider here. And we don't have to worry about variations in one affecting the other. So I think, as I already mentioned, that LSB notation is telling us what the smallest step size you see in the ADCs. That was just a slide with that. The resolution stuff I went over. The other thing you'll see specified is the conversion rate. And this is always done in samples per second. So this is how many times per second it's sampling the world and giving an output. So you'll often see like kilosamples per second or megasamples per second or gigasamples per second. So this is just CD quality audio is something like 48,000 samples per second, so 48 kilosamples per second. On your oscilloscopes, you might see, like 100 megasamples per second, so 100 million times per second. It's sampling the system. To actually do the conversion, there's quite a few different types of ADC or architectures. I'm only going to cover these first two. So these are probably the most common. This is the fastest. And the second one is what is in AVR. So it's the one that you'll have the most use with or experience with in this class. There's a bunch of other designs. So if you need stuff like a really slow ADC that's extremely high resolution, there's a delta sigma or sigma delta. People switch the word around. That's common. And a few other designs of various ADCs. General purpose, the successive approximation is quite common, so you'll see that in a lot of microcontrollers. For very, very fast, like if you're talking about RF basebands or oscilloscope front end, stuff like that, the flash converter is probably more common. So the parallel or flash converter here is shown. What it does, it just has a number of comparators, and all it does is it immediately generates an output voltage. So we have an input, so this is the signal, and then each of these converters is actually, or each of these comparators is actually 1 bit of the output. So it simply says, at the lowest end, is this higher or lower than some threshold? And this directly generates our output code. The main downside of this is that you require, you need one comparator for every bit of the output. So if we're talking a 7 or 8 bit ADC, it's not quite so bad. But if we're talking 16-bit, 18-bit ADC, it can get fairly excessive, and it takes quite a bit of silicon. So a more sort of common design is the successive approximation. Basically, there's 3 diagrams here showing different aspects of the design. The very basic design is this is our input voltage here, and it actually uses another component we'll talk about, a digital to analog converter. A digital to analog converter generates an analog voltage here. And it has a little bit of logic that effectively does a search tree to figure out what is that input voltage. So it would first try, the lowest bits. So this here is showing the DAC output. So this is this line here. So what's going to happen is that the DAC is going to start at 0 volts and say, is this higher or lower than 0 volts? If so, it can then do a search where it says, is it lower than whatever my maximum threshold is? If it's lower than my maximum threshold, it's somewhere in between my 2 ranges, so it's not over range. And it then jumps to halfway. So it says, if I set this input to 2.5 volts, is it higher or lower than 2.5 volts? If it's higher than 2.5 volts, it then goes halfway, so it's just binary search. It goes halfway between 2.5 volts and 5 volts and says, is it higher or lower than that? And so on. So what you'll see is that it's basically doing this search where if we had, so this dotted line is the actual voltage. So it's going to slowly sort of approximate, do the binary search correctly here. So it's going to start at 0 volts and say, is it higher or lower than 0 volts? It'll say higher. So it'll go to the other extreme and say, is it higher or lower than, my maximum voltage? And the comparator will say lower, so it'll go halfway. And it says, is it higher or lower than this point? And it says higher, so it then goes halfway again. And you can see it's just slowly doing this, this search to find what the actual output voltage is. So it'll say, okay, is it higher or lower now? Lower, halfway, and then each time it's sort of going halfway. And eventually it's going to achieve success relative to whatever the resolution of that digital to analog converter is. At that point, it knows what the output voltage is, so it's done, or the input voltage. So that's all of the successive approximation converter does, and there's, it has an example of the logic is checking all the bits. One other thing you'll occasionally see is what's known as time interleaved ADCs. So how this works is if you have a bunch of ADCs and you need to very quickly sample a signal, so if we have some signal here, what you can actually do is you can configure it such that what I'm going to do is draw them in different colors. ADC. And these ADCs aren't fast enough, so if you need gigasamples per second or something like that, and you can't get that sort of ADC, or you have a number of slower ADCs available in your system, what you could do is choose to sample, choose to sample using each of these with a slight time offset. So if we have a sample clock here, it goes to that ADC. So we have a delay to this ADC and a larger delay to this ADC. And so what you'll see is that samples occur, here, 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 and here. By the red ADC, they should be very constant time. I'm sort of making a quick drawing here. And then the blue ADC had a bit of delay before it starts sampling, and it samples at the same, interval in between. And what we're able to achieve is that at the end of it, by combining all these samples, it has a even faster somewhere. I don't know, it should be below. Something like that. So the time between any two successive samples will be a lot shorter than any of the individual ADCs. So some of the issues with this are that each ADC input might be a little different in terms of performance. So how linear the input is, you may have errors in that actual measurement time delay there. But it is a simple method of achieving a higher sampling rate than you could otherwise achieve. So the flip side of the ADC is the DAC, or digital to analog converter. So the DAC, there's two main types that you can implement. The first is what's known as a resistive ladder. So a resistive ladder uses a series of resistors, shockingly, to generate the analog output. And you can see the format here. We basically have, when it says R and 2R, it just means double. So if this is a 1K, those are just 2K resistors, something like that. And all you do is you set the inputs to 0 or 1 to generate your output. So it shows it with switches. You could just connect this to your AVR port pins and say, I want an output of 0, 1, 1, 0, 1, 1, 0, 1. And where a 1 is really just a 5 volt. So it either connects this to 0 volts, 5 volt, 0 volts, 5 volt, 5 volt, 0 volt, whatever it was, that's not the same code. But you can then see that what it'll do is it's going to generate an output that's relative to that code you put in it. And you can sort of intuitively see that what it's calling the MSB here is the closest to the analog output. So if you set this to 5 volts, it has much less impedance. Look, before it gets to the buffer, this is just a buffer here. The buffer output compared to, say, if you twiddle the least significant bit down here. So the LSB is going to have much less of an effect on the final output, and in fact, it'll have the smallest effect compared to the most significant bit on that side. And if you go through this, it actually does work out exactly like you'd expect for a DAC. So twiddling the most significant bit will give you, a 2.5 volt jump, and twiddling the least significant bit should give you the 1 over, how many bits is this? Is this 8? 1 over 256 volt change. So that's sort of a simple DAC you can build. The main downside is it takes 8 port pins here. So it takes a lot of pins to do this, and you might not have a lot of extra pins in the AVR. The other thing you can do is use this pulse width modulation, which you experimented a bit in the motor control lab. So what this requires is that you design a low pass filter. So if you do the AVR, and you would design this low pass filter to be, keep forgetting that's off page, let me move that down. So AVR, this is output voltage. And so you have to design the low pass filter to, it depends how quickly you want the output to change. So if you're just setting a voltage and letting it settle, this could be like a 1 hertz. Come on. What is happening? Sorry. That could be like a 1 hertz roll off. Okay. There we go. Without issue. So if that was like a 1 hertz roll off, you don't care because you're not trying to change the voltage very fast. And then you could drive it. Your pulse width modulation frequency could be like a kilohertz or something fairly safely. If you wanted to use this to generate audio, though, you would need something like a 20 kilohertz roll off there. And your pulse width modulation frequency must be much higher than that because you don't want that frequency to leak into the output. So then you might need 100 kilohertz pulse width modulation frequency. So in the bottom here, it shows a diagram showing, if you have a very narrow pulse width, you get a low output voltage. And you do see some ripple, so you can see some ripple in the output here, and that's based on the roll-off frequency of that low-pass filter, allowing a tiny bit of the pulse width modulation frequency to leak into the output. So there's a trade-off there depending how quickly you need to generate the signal. But the advantage of this, it only took a single port pin. So previously, we took 8 port pins, and now we only need 1. If you want to generate a very high resolution signal, so if you want like a 16-bit digital to analog converter, it is possible with this because the AVR does have some very high resolution phase modes. And so you can get a pretty good digital to analog converter with just a single output pin. It might not be very fast because of the requirement to have a very low roll-off frequency in the bandpass filter. But a lot of the time you just want to set a reference voltage and that's it, and then you're done. All right, so that was all sort of, very generic. Now I want to move into using the ADC in the processor itself. So the ATmega644 ADC, it has 10-bit resolution, and I want to show you the data sheet so you know whereabouts to look. Wow, it's huge for some reason. Anyway. Here's full screen. So if you look in the data sheet around this chapter 21, it goes through both everything about the ADC and using it, and various, examples and stuff like that. So everything I'm talking about here is going to be pulled from this section, but you can look through, it has quite a bit of background on it, errors, how to convert everything, before it gets into the details of it. So that's a really good resource. A brief overview of the ADC. So it uses that the SAR format we talked about, the successive approximation. At the input, it has an 8-channel multiplexer. So what this means is that the ADC itself, there's only one ADC in the AVR. There's a single ADC. But there's actually 8 input pins that it can switch between, and this is all the port A pins on the micro, and basically it just has a switch, and so you can say, connect port A0 to the ADC. So you can't do 8 conversions at once, but you can say, convert this, then convert that, then convert that. The ADC itself can run it up to about 100 or 200 kilosamples per second, so it's more than fast enough to, quickly switch between all these channels, even if you want to do filtering on each channel and stuff like that. For most of what you're doing anyway. So it is quite good in that regard. It also has 16 differential inputs. So these inputs, it actually does more than just switch between them. In reality, what we have is there's sort of, these 8 inputs. And it also has some various other logic. So it can do these differential measurements. So the advantage of a differential measurement is if you have 2.1 volts on another channel, on one channel and 2 volts on the next, it can tell you there's 0.1 volts of difference between them. It can also add some gain after that differential measurement, so that you can measure very small differences between the 2 port pins. So this can be really useful in situations where you have what's known as like a bridge configuration, or in your case, what you might have is if you have 2 sensors, like 2 variable resistors, for example, and all you care about is what's the difference between these measurements. You don't care about the absolute value, only the difference. It also has options, so we talked about needing to specify the VREF, the reference voltage. So it has built in a few different reference voltages you can use. It can also switch in external reference voltages, either an external pin or the VCC voltage. And there's also the various operating frequencies and interrupt types that we can use. All right, so this slide that you probably just see, this is just pulled straight from the data sheet. Let me switch to that so you can see it a little better. So this is showing you the ADC itself. So at the bottom here, what you can see is there's the ADC inputs. So this is those 8 input pins, the port A pin 0, and into this we throw the input mux. So this is where it's selecting what pin to use. It actually, you see these pins go to 2 spots. They go to a negative and a positive input mux. So what this is that if you're doing the differential inputs, it's actually switching to the gain amplifier here. Let me just turn on drawing. Okay, I forgot I don't have it on this computer. One second. Where is it? don't know. This one had some weird version of it that didn't, because normally it did let you. There we go. Oh, fill in sign maybe? Okay. So I don't need it anyway, just to show this stuff. So you have the gain amplifier, which is if you have a differential input, so you're saying what's the difference between port A0 and port A1. You can then choose to add some gain before switching to the final ADC. So all of those blocks are just the muxes. So these sort of 3 blocks here, you see the 10-bit DAC, the sample and hold comparator. So sample and hold simply means that your measurement's going to be changing in time. So it picks one time. If you remember going back to how the SA error register works, where is it? It's doing this successive comparison. If your analog voltage was changing while it's doing that comparison, this will be very not good for the ADC, because it's going to be continuously hunting for a value that is changing. So to get around that, the sample and hold input ensures that it samples your input, holds that value, and then does this comparison. So that's what the conversion logic does. The conversion logic itself has a few things we'll care about. One is the prescaler. So this selects how fast your ADC clock runs. So this is how quickly we're doing those conversions. The other thing we'll have here is we'll have some status and control registers. So we'll look at how to set those up. And you also have the triggering. So the triggering defines when does the ADC start doing a conversion. Once it's done a conversion, it puts the results to this ADC H, ADC L. So this is just the output register. So that's kind of everything we care about there. So let's look at details of the settings. All right, so the first thing is the clock setting. So it requires you to define, so we have an input clock. This is your system oscillator, the 14 point some megahertz. And you have to configure this prescaler to generate a clock source that is between 50 to 200 kilohertz to get the best results. So you'll have to go through and say, okay, if I have a 14 megahertz clock, what do I have to divide it by to get anything in vaguely that value? Once you have that, the next option is what the reference voltage is. So as I mentioned, there is a few options here. And let me pull the data sheet up so I can move it up here. So there's a few options here, and basically some of the ones you should care about is in AREF, internal VREF turned off. This means there's an external pin that's physically called AREF. This is sort of the default, and you will then have to put a voltage on AREF at most 5 volts, so don't go crazy here. Typically this means you'll just have a bridge between AREF and AVCC, or the 5 volt output. The other option, if you don't want to use a wire, is you can actually enable, if you set ref as 0 to 1, and this is what I do in some of the example labs. The chip itself shorts the AVCC pin, the 5 volts, to the AREF pin. And so you don't have to physically connect anything to it, and you'll be fine. So this gives you a 0 to 5 volt input range. If you don't need such a large input range, if you know your sensor only has more limited output, it goes from 0 to 1 volt, 0 to half a volt, you can use either of the next two options. And these options actually put a lower voltage on the AREF pin, and remember that means that our ADC input still has the 1024 counts, but it's now split between a smaller number. So it's split between 0 to 1.1 volts or 0 to 2.56 volts. So it improves the resolution in terms of how many millivolts can we detect. And there's also, and there's typo in their data sheet, but whatever. If you use the 10 times or 200 times gain modes, this is where you're using that differential input. There's certain restrictions on what you can use as the voltage reference. In that case, you can only use the 2.56. You don't have a choice. So there is various other restrictions you'll get into, or reasons you might not want to use modes. But generally, one of the first two are probably what you'll use. Come on. Where is it? For some reason it's gone crazy on me here. All right. So generally those are the first sort of the modes you might need. And I really want to emphasize again that AREF is a physical pin, so when you plug it in, you can see right there, it says AREF. So if you are deciding to set the AVR up to physically use the external reference, you'll have to wire that to 5 volts or to your sensor power supply or something else. If you're not using that, then don't connect a wire. So only drive the pin when you have this case. The ref S1 is equal to ref S0 is equal to 0. If you're pulling in someone else's ADC code, always check what they're using. Because if you power the pin and the AVR is also attempting to put a reference voltage on it, bad things will happen. So once you have that, you've got the clock, you've got the reference set up. The only other thing you need to do is set up the multiplexer input. So the multiplexer input, in the most basic format, selects between what are known as these single-ended ADC channel, ADC 0, 1, 2, 3 to 7. Each of these, by the way, is equivalent to, so this is port A's pin 0. So on your little digital trainer, ADC pin 0 is down here, this PA0. So that's ADC 0. This is ADC 1, etc., all the way up to ADC 7. So those are the analog inputs, is the lower, the port A pins. So you can select which of these channels to set up. Alternatively, you can use if you use differential mode, so you can see towards the bottom, it starts having some of the options to say, well, subtract ADC pin 1 from ADC pin 2 and multiply it by 10 times. So this is where we get the differential modes with gain. If you use these modes, remember the deal with the VREF. You have to use this 2.56 voltage reference. So if you want to use any of those differential modes, be aware of that. And you'll notice one of the options, which at first you see, why do they do that, is positive and negative both go to ADC 0, for example. And why they do this is that this is to determine what the offset error is. So really what you're doing here is we have the input differential and it's shorted together to the same voltage. Just an output. We don't care what the output is. And then it goes to 10 times gain and then to your ADC. These stages won't be perfect. There's going to be some offset voltage. So by shorting it together, you can measure what that offset voltage is and then subtract it, and then you would switch to, okay, I'm actually measuring between ADC 1 and ADC 0. So that's why you'll see this sort of weird positive and negative input with the same input connected to the differential amplifier. But most of the stuff you do will probably be the single-ended input, but you can play with the differential. You may find it useful for a few sensors. All right, so simple example here, selecting channel 1, so port A.1, not dot 0. What we could do is we could say AD mux, so the AD mux register. This is from the data sheet. The lower 5 bits, this is the channel select. So what I'm going to do is I'm going to take the value of AD mux, and I'm going to do this. I do this bitwise and, so E0 in binary is 111000000. So what this means is I want to keep the top 3 bits of 80 mux. I need to keep those bits because maybe I configured my reference source. This is the reference select. I want to not modify those, but I want to clear away the lower bits and then select my new channel. So this is the new channel. Single-ended channel 1. And that's from the data sheet saying the single-ended input, channel 1. All right, so that gives me a channel. The only other thing, so then we can do the conversion and get the result. We also needed to do a few other things before that, so that was really only that one, configuring the input. Enabling the ADC and configuring the clock, as mentioned in the data sheet. I'll talk about that. And we also need to trigger it. Close the door to see if that. I don't know if that will really make it any quieter. We'll hope. All right, anyway, trigger it. Once we trigger it, we need to wait till the ADC is done and finally read the result. So a really basic example, and some of these are pulled from my 3204 lab, so there's a reference to that lab. Or in the 3901 course, on the Blackboard course, there's an option that says like code samples or something like that, and it has a bunch of ADC examples. So we need to, I mentioned before, we need to select an ADC clock. So I'm going to divide the 14 megahertz clock by 128 to give me a 100 kilohertz clock. So this is in that 50 to 200 kilohertz range. Approximately, that'll be fine, as long as it's close to that frequency. So that's what these bits are doing. The other thing we need to do is we're turning on the ADC. Turn on ADC. So we've set this AD enable bit. So that's in status register A, status register B. The defaults are fine, I just write 0 to it. So it puts it in what's called free running mode, where it can always run. And then the AD mux, I'm going to select what is the channel. So if I set AD mux to 0, if you go back to the data sheet, what this is going to say is it's going to do a few things. It's going to select ADC 0 on the single-ended input, and it's going to select the AREF pin. So to use that example, I'll have to wire 5 volts to my AREF pin, or I won't get a proper signal. And the final thing I'm going to do, there's this special register DID-R0. This is disabling some of the input buffers on port A. If you set this, you can no longer read the digital status of the pin, but it improves the current consumption. Basically, when you're putting an analog signal into the ADC, the digital circuitry is still trying to read, is this a high or low signal? This can result in higher current consumption because the input buffers, the digital input buffers, aren't designed to accept, analog signals that are halfway between high and low. So you can just turn those buffers off. You won't damage anything if you leave them on. You just may have, slightly higher current consumption. So in general, it's a good idea to get used to turning them off. All right, so now everything's set up, and we can really easily just do this code. So what it's doing, it's setting this start conversion bit. So this tells the ADC, hey, do a reading. Once we do a reading, just wait until it says it's done. So this ADIF bit says that the ADC is done. It takes a little bit of time to do each conversion, so we've got to wait for it to complete. Once it's complete, we clear the bit. So this looks a little funny. The ADC SRA, if you go through the data sheet, it's what's known as a set to clear register. So in order to write that bit to 0, we pretend we're writing the bit to 1, and the microcontroller clears it down to 0. So we need to do this in order to check, next time we run this through, to check that the conversion was done. If we don't clear the bit, this loop will right away say, all right, oh, your ADC's done. And you'll be reading the old results because you never cleared that bit. So that's why we have those lines of codes. And finally, we can just get the reading. So I had to declare a variable somewhere. And to get the reading, we just read this special ADC register. This ADC register is actually, if you remember, we had a 2 to the 10 bit ADC. Therefore, it's more than just 8 bits. So it comes across as a 16-bit register. So it's sort of to break out that and a few other caveats. Every time you change any of the ADC settings, so when I change the AD mux or something like this register, which means I've changed either the VREF or I've changed what channel I'm using from, it's worthwhile to throw away 1 or 2 conversions. I actually like to do 2 or 3. So this basically means I would just do this 2 times. Why you're doing this is that you may have previously started a conversion with the old setting before the system had actually changed what the input mux was. That conversion is going to be garbage because it has the wrong value in it. And it may be that you didn't wait long enough after changing it. You can see the data sheet for how long you're actually supposed to wait in terms of ADC clock cycles. Or it might have had an old conversion already in the pipeline. It might have already done a conversion before you even changed it, and you're going to read that old value. So it's always useful to throw away, just do the readings and don't actually check the values, throw them away. As I mentioned before, we're disabling the digital input to improve power consumption. And the final thing is that ADC, it's actually 2 registers. There's an ADC-L for the low byte, ADC-H for the high byte. You always have to read both bytes to get the value cleared away. So even though you may only care about one of them, the system is expecting you to read both. The easiest way around this is that if you just read from ADC like this, the compiler is actually taking care of reading the low and the high byte for you and combining them together. So here we had the case where we have a 16-bit, or we have 2 8-bit values, and we can use one of those 8-bit values only. Here we don't have that issue. We have a 16-bit, what's effectively a 16-bit value we can just directly use. So I tend to recommend doing that. The compiler deals with accessing both registers for you and gives you a nice value you can use. All right, so the other thing you can do is you can start setting up automatic, and this is using the interrupts. So the interrupt system in the ADC will just tell you when it has new data. So rather than having to wait, you can set up this interrupt service routine, this ISR here, to get new data. So to do this, well, you can ignore the DDRC. Originally this was outputting it to port C, you don't need that. So we do the same setup. So we set the ADC mux here, analog input 0, VREF is external, blah, blah, blah. So the only other thing we do is we actually enable the ADC interrupt, and we still have this free running mode where it's automatically triggering. Once we enable the ADC interrupt, what's going to happen? Every time the ADC gets an interrupt, it's going to jump here and say, hey, you have new data available, and it's up to you to then read that data. Immediately, the ADC has started doing the next conversion, so it's already started to reread the value. So sort of some of the caveats here are that you're just going to keep getting interrupts with new data. It's up to you to switch channels. Which is to say, you can say like, oh, actually, I want you to read, channel 0 10 times, then channel 1 10 times, channel 2 10 times, etc. If dealing with the switching channels, one problem you might have is that, you can't just read channel 0, then 1, then 2, then 3, because by the time you start to try to switch channels, it's already started a new conversion. So this is where you'll have to integrate logic to throw away a few conversions or stop the ADC, change channels, etc. Throwing away tends to be the easiest. You just keep it running, change channels, and throw away the bad conversions. you may need to have what's known as atomic operation. So what this is that if we just had this logic here, so I have a global variable called new data. The problem is that this interrupt service routine could be jumped to at any time. You know, it's going to be however often the ADC is running, finishing the conversion. It's going to jump to that and write a new value of the data into the ADC register, or into this global variable. If I'm using that global variable at the time, the compiler, the AVR doesn't care. It's just going to jump to the ADC and write a new value into it. You know, so in my code, I could be having something like if new data is lower than 728, you know, do this. The problem is that midway through this comparison, because this is a 16-bit value, so it's actually 2 bytes, midway through doing the comparison, I could jump here and overwrite that value with something new. And then it's going to jump back to my code and finish doing the comparison. And it doesn't know that half of the data has changed because it got halfway through doing the comparison. To fix this, you might need what are called atomic operations. So atomic operations stop the interrupts when you're doing this chunk of code here. Or even better is to use something that when you get the new data, you push it to a queue. So you say, here's some new data. You know, you have a 16-byte array or something like that, and you just add data to that array. Your main code then pulls the latest data from that array and doesn't have the issue that it's overwriting some global variable like this. These are the sort of errors, these global variables, overwriting them. They're the sort of thing that, yes, it won't happen all the time, but it'll happen very rarely and be very hard to debug. So it's worthwhile thinking ahead of time what will happen if, you know, an interrupt happens anywhere in my code, and then it jumps to the ADC and gives me new data. And the final thing to think about is possibly doing some filtering. So you could get, you know, you could easily get 10 readings from your ADC per channel. And you could do something as simple as just averaging them out. You can get more advanced implementing filters in software, which I'll try to talk about in a few weeks. But at bare minimum, you may want to just add 10 samples together and divide them out to give you sort of an average. So remember, you're only getting the count, so you're getting this ADC value. It's up to you how you interpret it. Everything can be converted from a voltage. This is the input voltage. And remember, we have the Vref. So basically what we do is we split between 0 and Vref into 1024 counts. And the ADC value is the count number relative to what your input is related to the Vref. So you can reverse this to get a voltage back directly. What's sort of easier, you probably don't care about the exact voltage you got. You'll probably just be scaling it to some other factor. When you do the scaling, be pretty careful of, you know, overflow or rounding error. So maybe you have some, you know, level in meters of fluid is the ADC count times 89 divided by 15. The problem here is that ADC count ranges from 0 to 1024. Well, if it's at the higher end, if it's 1024, times 89, you know, this is going to be greater than the value you can represent in a 16-bit number. So you're probably going to get overflow. So to save this, what you need to do is cast, so use the C casting to cast these intermediate values to 32-bit numbers. So you need to consider what's the largest number I'll get within my operation. Now that it's a 32-bit number, I won't have this overflow error anymore. The other issue you could get is interdivision. So let's say level M is floating point. I've decided, you know, screw it, I'm going to use floating point. What's going to happen, though, is the compiler sees ADC. This is an integer. It sees 1024. That looks like an integer. And it's going to do integer math. That ADC is always going to end up being 0, the result of this equation. Or almost always, because this is, you know, unless it's equal to 1024, which it won't be. So if you read 1019, so you read a very high value on the ADC, it divides it by 1024 using integer math, not floating point. So in integer math, you effectively round down. That's going to just equal 0. And it's going to multiply it by 4.5, and you'll still get 0. So to fix this, it's pretty easy. You would cast the ADC to a floating point. Again, if you want to use floating point, it will be slower. And then the 1024, I'd also cast to floating point. An easy way to cast to floating point is to add, if you add a decimal, so in this case I added the decimal 0, it just tells the compiler, hey, this is floating point. That's sort of a little trick. And then this will work. All right, so basically the conclusion of the ADC, it's probably going to be a very major part of your robot. There's a lot of various sensors you can use it with. So I suggest you sort of start experimenting if you haven't. 2 resources. There's a lab from the 3204 course that I go through. And again, there's sort of a video on this. Just very basic example using the ADC and printing the results to screen. You can go through this as a first step. Once you have this, you can even use this sort of code to interface to your sensors and say, oh, how do the sensors work? Can I print to screen what the readings are? The ECED3901 code samples on BBLearn. There's some more ADC examples. And there's lots of AVR ADC examples online. Before we finish, I'll mention briefly on Monday, the lab, so all of the official labs and assignments have been given out now. There's no more stuff that will be marked besides your progress report, which hopefully everyone remembers about for next week, and the final report. So the lab on Monday is optional, as well as the following ones, but basically if you want help with your robot, I suggest coming, sort of figuring out something you can work on. The one thing we will do, I'll go through on Monday in the lecture, how you do printed circuit board layout. In the lab, we'll be designing a custom printed circuit board, and I've got to confirm with Mark, but the plan is we're going to submit them for a production run. It'll take about a month, so you won't be able to use it in your robot, but it'll be cool because it'll be something you made, you put your name on it, whatever you want. Put I am awesome, just write it across. And you'll physically get this back, and you'll have a little board, show people how cool you are in a group, and you'll get a few copies of it. So we'll go through how that works, and more importantly, to some degree, how you can do this on your own. There's a number of very, very cheap places that for like $14, you can get a whole bunch of these circuit boards back. So it's a really good resource if you're experimenting a bit and want to test out your own circuits. We're going to be using Eagle. That's what they use in the labs. You can freely download a version of this legally. It's for non-commercial use, completely free and capable of doing everything we need. If you've never used it before, I kind of suggest checking out some of the online tutorials. Some of the interface, it's improved over the years. It's a tiny bit crazy compared to sort of a more new software. It's become a lot more user-friendly, but it doesn't hurt to familiarize with it. There's a lot of tutorials online. It's very popular. I'm going to go through it on Monday and in the lab anyway, so you don't have to, but it might give yourself some time. If you don't, I mean, as this is optional, you don't have to submit it, but there will be sort of a strict deadline of 1 week after the lab to have a board, and you have to get it to Mark in time so he can submit stuff for to have them made. So that's the only reason I say it's useful to familiarize yourself with it, just to make sure you have time to use it. So with that, are there questions on that or other stuff, such as the progress report, or no? All right.